So today is the last lecture of the course, and I will try to do my best to finish the theory. So we are doing the last part of the course, which is called Stechmüller TQFT. I will try to formulate the theory in a form which can be used for calculations, but I will not spend time on explaining the formal properties of it. So let me recall what we did last time. So we interpreted the tetrahedral weights. We've taken as tetrahedral weights the integral kernel of the operator W hat. So we had x1, x3, W hat, x0, x2. And we started calculation of this kernel, but we didn't finish. But the result was asked to finish at home. And I hope that you calculated this answer. So there is a one delta function. There is a exponential factor 2 pi I x0, x2 minus x3, and times another exponential factor pi I x2 minus x3 squared, and the Fourier transform of the function phi evaluated x2 minus x3 tilde. So where W hat is phi of q1 minus q2 plus p2 with operator argument minus 2 pi I q1 q2. And phi tilde of x is integral phi of y e minus 2 pi I xy dy. So the distributional Fourier transform. And in principle, if you take any function phi, the integral kernel will be like this. But for us, important choice phi of x is a Faddeev function, which verifies pentagon, and then we can we've seen that we associated to tetrahedron with ordered vertices by 0, 1, 2, 3, and the face is colored by variables x, and the indices correspond to opposite vertices, the x3 here, x2 here, x1 here, x0 here. So we can think of this. But in principle, we have two kinds of tetrahedra. This is a positive tetrahedron. Positive. But we have negative one. Negative, which is same, but the embedding into 3 space cannot be related by rotations in the space. So we put in the center 0, in the top 1. But if in the positive case we go counterclockwise when we go along 1, 2, 3, then in the negative case we go clockwise. So we go like 1, 2, 3 like this. But we put the arrows with the same rule. And so the only effect is that the bottom arrow is swapped. Okay, so this is negative. But if we keep the same coloring, so we put x2 opposite to 2, x3 opposite to 3, x1 opposite to 1, and x0 opposite to 0, then the associated weight function will be complex conjugate of that one. Complex conjugate. And by using the rules of calculus in the Hilbert spaces, this is the same as a matrix integral kernel of the conjugate, Hermitian conjugate operator, W. But you should not forget that on writing this equality, we swap the input and output. Okay, so if x0, x2 were as an output or ket vector, then in the right-hand side it becomes a bra vector and so on. Okay, but in the case of this choice, so conjugate is W minus 1 if phi is equal phi b. But we will talk about a generalized model where instead of phi, we will take a family of functions where phi b will be just one member of the family. So this is not the ultimate formulation of the TQFT. This is just a particular case. So we will call x0, x1, x2, x3 are state variables. State variables. Okay, so what we are going to do next is to generalize this system, and I will explain where it comes from, this generalization. So proposition. Today is lecture number 13, proposition 1. Okay, so let us take for any alpha, beta, gamma in open interval of length pi, such that alpha plus beta plus gamma equal pi. The functions, the Schwarz class functions, phi. So I put alpha gamma, but because they are dependent, so we can solve, for example, for beta this relation, and then we leave just two variables. So phi of so this is a two-parameter family of functions which will include this function, and then it is defined in the following way: the Faddeev function evaluated on x plus imaginary part, which is I pi delta, no pi, delta of alpha plus gamma, E. Unfortunately, I'm not sure about, 2 pi delta alpha x, 2 pi delta alpha x, functions where delta is a notation for b plus b inverse over 2 pi. Yeah, so is such that So phi tilde of alpha gamma of x, which is by definition a Fourier transform, ye minus 2 pi I xy. And it is calculated as a zeta 0 of alpha gamma times phi gamma beta of minus x e minus pi I x squared. Zeta 0 of alpha gamma is a function on unit circle, which can be calculated explicitly, but for us it will not be very important. Okay, so that's the first relation. And second relation, the complex conjugate of that, of alpha gamma, is a phi of gamma alpha of minus x e minus pi I x squared, with another zeta 1 of alpha gamma. Zeta 1 of alpha gamma, again, is on the unit circle. Okay, that's a proposition, and so the idea of proof. So we take a complex Fourier transform, phi tilde of yes, Fourier transform of Fourier function, phi tilde of z is r plus I epsilon, phi b of u e minus 2 pi I uz. Right? That's the integral which we studied actually, which is absolutely convergent. Absolutely convergent if 0 is less than imaginary part of z, less than epsilon, less than, let me use this notation, pi times delta, right? So that was a domain of absolute convergence but the last equality actually is just to keep this contour away of the poles. And so we parameterize epsilon as a delta times alpha plus gamma, and imaginary part of z as delta times alpha. So if we substitute this, what we get? Then the inequalities star are equivalent to what? We have a 0 less than alpha. So I divide by delta, right? We can divide by delta the whole inequality, less than alpha plus gamma, less than pi. So we see that alpha, gamma are in the unit interval, not the interval open interval 0 pi. But there is one extra condition, that beta is also in that interval, where beta is defined by pi minus alpha minus gamma. So this is equivalent to exactly the condition we put in the statement of proposition. But on the other hand, we know the Fourier transform of phi function. And so we can calculate it. So let us see. Now phi b tilde of z becomes an integral over real line. So we shift by epsilon the variable of integration. So we get a phi b of y plus I epsilon. Right, e minus 2 pi I y plus I epsilon. And now I'd like to use this parameterization. Okay, so let me put x plus I delta alpha. So I denote x by the real part of z. This is the imaginary part. So here I put the x plus I delta alpha dy. And now you can see that looking at the definition of phi alpha gamma, what we see here is that the integral of phi alpha gamma of y, and we have this Fourier transform minus 2 pi I xy, and then something else. And something else is y independent. Let me see if I have this. Yeah, so times e 2 pi delta alpha plus gamma x plus I delta alpha. So here we have a phi tilde alpha gamma of x. So you see that by introducing phi alpha gamma, we up to multiplicative factor, which is x dependent. For the Fourier transform, we get the Fourier transform of phi alpha gamma, just explicitly. And then this dependence on x can be put to the left-hand side to convert, using the explicit form of the Fourier transform of the phi j function, we can convert eventually it to this equality. And likewise, second one, which is easy actually, you just complex conjugate and verify. Okay, so likewise, this is equivalent to 1. And likewise 2. Okay, so I'm not going to spend any more time on that. And based on this, we define now angled tetrahedral weights. So we pick up let alpha, beta, gamma in open unit interval cube. Okay, and we define angled tetrahedra. we put those three variables on the edges of the tetrahedron. So let me put it 0, 1, 2, 3, for example, positive tetrahedron. And of course, we have state variables as before. But additionally, we put angle variables on the edges. So we put alpha on edge 0, 1 and edge 2, 3, which are opposite. And then we put beta to 0, 2 and the opposite 1, 1, 3. And likewise the gamma to 0, 3 and 2, 1. So in principle, one can think of alpha, beta, gamma as dihedral angles of an ideal hyperbolic tetrahedron. So, and then the same thing for negative, right? For negative 0, 1, 2, 3. At 0, 1, we got alpha, beta, gamma. But you see that they arrange differently. So what we use for arranging the variables, the enumeration of the vertices, not the way we draw it, right? So beta always is associated to 0, 2 edge. And in the upper picture, it is here, while in the lower picture, it is here. So this is positive, negative. Okay, so that's pictures, and then the tetrahedral weights, angle tetrahedral weights. Angle tetrahedral weights. So in the case of positive, so let me call it W of positive T, positive tetrahedron, angled tetrahedron T. So we have a Z of T X in state X. Okay, so X0, X1, X2, X3. So this X's are state variables, so I call it in state X. So this is the X1, X3. So the same formula, but with the only exception that now W becomes a W of alpha gamma. Or W of alpha gamma hat is the same formula, but with phi replaced by phi alpha gamma. Q1 minus Q2 plus P3, P2 E minus 2 pi I Q1, Q2. And negative tetrahedron, we put Z of T X is equal complex conjugate. Okay, the same thing, but complex conjugate as before. Or the same thing as X0, X2, W alpha gamma hat Hermitian conjugate. X1, X3. And just a remark is that the actual calculation x1, x3, x0, x2 is calculated like a delta of x0 minus x1 plus x2 e 2 pi I x0, x2 minus x3. And then we have a functional part zeta 0 of alpha gamma. There's a phase factor, which we didn't specify explicitly, phi gamma beta of x3 minus x2. Okay, for calculational purposes, this formula is very convenient. So it has an explicit term. So you see, the tilde has been absorbed by using the proposition. Right? So we write W alpha gamma in terms of function phi alpha gamma, as well as the integral kernel itself. But the variables get replaced a little bit. So you see, if on the W level we have alpha gamma, on the operator kernel we have phi gamma beta. So there is such transformation rules. So let me put it as two remarks. So that was the first remark. Second remark, the angled tetrahedral weights satisfy the angled 2-3 Pachner relation. And what is it? So we just draw, as we did last time, a picture for Pachner moves. So enumerated in a specific way, 0, 1, 2, 3, 4. Zero, 1, 2, 3, 4. You can put also arrows. And we have but everything now is angled, right? So we have 5 triples of angles. We have alpha I, beta I, gamma I, right? In 0 pi, open cube with a condition alpha I plus beta I plus gamma I equal pi, where I takes values from 0 up to 4. Up to 4. So, for example, alpha 3 is associated to upper tetrahedron here. So we write 0, 1, 2, 3, 4 for the set of labels. And then when you close one of the elements in the set, you get a quadruple of elements which specify a tetrahedron, right? And then this tetrahedron will carry the angles alpha I, beta I, gamma I, where I is the integer which you closed up or you thrown away. Okay, so here, for example, at this age, there will be alpha 3, because the tetrahedron is a 0, 1, 2, 3, 0, 1, 2, 4. So the 3 is closed up. And this is the first edge, 0, 1. You remember our rules. Alpha is put to 0 and the next vertex in the linear order. So this will be alpha 3. While here, this edge is shared by 2 tetrahedra, namely tetrahedron 2 and tetrahedron 4. And for both of them, it's an alpha angle. So this is alpha 2 plus alpha 4. Right? Do you understand? So, so look, 0, 0, 1, right? H 0, 1 belongs to tetrahedra. So if we close this 0, 1, then the remaining indices will give the tetrahedra to which it belongs, to tetrahedra 2, 3, and 4. And in the left-hand side of the equality, only tetrahedron 3 shows up, while in the right-hand side, only tetrahedra 2 and 4 show up. Right? Because this is a tetrahedron T3, lower one, tetrahedron T1, right? It's opposite to 1. And in front of us is a tetrahedron 2. And then the back tetrahedron on the left is tetrahedron 4. And this tetrahedron on the right is tetrahedron 0. T0, T2, T4. Okay, and then let me put it T2, T3, T4. And so the relation is alpha 3 equal alpha 2 plus alpha 4. And then we can consider age 1, 2. 1, 2. Then it belongs to what? To tetrahedra 0, 3, 4. And so let us see 1, 2. What is 1, 2? It is opposite to 0, 4 in tetrahedron 3. So this is a gamma 3. Gamma 3. And here it is shared. It is shared between T0 and T4. For T0, it is alpha. So it is alpha 0 plus. And for T4, it is opposite to 0, 4. So it's a gamma 4. So the corresponding relation is gamma 3 equal alpha 0 plus gamma 4. And likewise, 1, 0, 1, 1, 2, 2, 3. So I omit the details. I just write the equations. So 2, 3 is gamma 1 equal alpha 4 plus gamma 0. 3, 4, alpha 1 equal alpha 2 plus gamma 0. No, alpha 2 plus alpha 0. And 0, 4, gamma 1 plus gamma 3 equal gamma 2. So these 5 relations are all these are all independent relations in the angled Pachner relation. And in particular, one of the consequences of this is a condition that the sum of angles around the interior edge 1, 3 is 2 pi. So 0, 1 plus 1, 2 plus 2, 3 plus 3, 4 plus for 0 or 0, 4 is a condition on around age 1, 3, which tells us that beta 0 plus gamma 2 plus beta 4 is equal to pi. So which means that the angle around this edge is 2 pi, which is geometrically very, very nice. Okay, and now, so before to formulate the theory, so I'm going to give a very long definition. Definition which will consist of six sub-definitions. Okay, so it will take, I don't know, 15 minutes. So before the break, we will not finish this definition. Okay, so the first thing is very basic thing, an ordered delta triangulation. So ordered delta I will often omit. This will be just a triangulation. But so we encountered this notion in the particular case of ideal triangulations already, but now we will put it into more general framework. So by definition is a CW complex X where each cell is given by its characteristic map. So alpha, which is a map from standard simplex to X. So the standard simplex, by definition, is a set of T0, T1, up to Tn in Rn plus 1 non-negative, satisfying the condition that T1 plus T0 plus T1 plus and so on plus Tn equal 1. So the standard topological simplex. And simplex. Okay, so in a CW complex, each cell is characterized by embedding of a ball into topological manifold, and this embedding, not embedding, continuous map, which is embedding on the interior. And so we think of standard simplex as a n-ball, and so we have such a map. And a part of this, so each cell is given by such a map, and for any phase map, and for any phase map, Fi, which maps delta n minus 1 to delta n, by sending T0 and so on, Tn minus 1 to T0, and so on up to Ti minus 1, then we insert 0 at i's place, and we continue with Ti and so on up to Tn minus 1. Okay, so we have a n plus 1 phase maps like this. And for any such a phase map, the composition alpha composed with Fi is also a cell. Okay, so which means that the interior of each phase is also embedded in particular. So that's the notion of ordered delta triangulation. It is also a characteristic map of a cell. Is also the characteristic map of a cell. Okay, so that's the first. Yeah, and just notation, which we used already. Notation xi is a set of I cells of X. Okay, so that's the first part of the definition. You see it took 5 minutes and 5 more definitions, but don't multiply 5 by 5. It will not. It will take less, I hope. Okay, to triangulate. So a triangulation X is called a triangulation of a pseudo 3 manifold or of a pseudo 3 manifold if X minus vertices is an oriented 3 manifold. Okay, so which is the analog of ideal triangulation? You remember that in ideal triangulation, so we considered punctured surfaces, but in the triangulation we added the vertices as 0 cells. So it's something similar. So we have vertices, but we demand only the complementary part for the vertices is really a 3 manifold. But any vertex, its regular neighborhood is not necessarily a 3 ball. It is a cone of a 2-dimensional surface. Okay, so that's why it's a pseudo, because of the spatial status of vertices. Okay, that's definition number 2. Definition number 3. Yeah, so a triangulation of a pseudo 3 manifold is called angled, shaped if all tetrahedra triangulation X of all tetrahedra of X are angled. Okay, so we have a shaped triangulation, and the weight of an edge E, so it's an element of X1, edge of an angled or of a shaped triangulation. X is the weight of H is a WE given by is a sum weight okay, WE of an HE is the sum of all dihedral angles around E. Okay, so if we have a HE, then WE is just the angle which we collect by summing all the angles around it. Okay, so this is the weight of that H. Number 5. So an H, a E of X1 of shaped X is called balanced, if its weight is 2 pi. W is 2 pi. Okay, so that's a balanced, and the longest part of the definition will follow. Okay, so longest last part of the definition, and then there will be main theorem of the course, and I'll try to describe then with a simple example how we do actual calculations in that theory. So let us continue. So the last definition gives the following. So two shaped triangulations are called gauge equivalent. X prime are called gauge equivalent if they coincide as triangulations, and there exists a map.
So do you mean they're isotopic or like?
No, just coincide. Just combinatorially, it's the same triangulation. Okay, so but prime, I mean the difference only on the angles. Dihedral angles are different. So even no isotopy needed, just the same. To show the triangulation, if they coincide as triangulations and there exists a map, a function f from going from edges to real numbers, such that so mu prime is equal sum of edges in X, f of E, okay, this function, and Poisson bracket with W of E of mu, such that, so where mu is any dihedral angle, mu correspondingly mu prime, respectively mu prime, is any dihedral angle of X, respectively X prime. Okay, so these two angles sitting on the same geometrical edge. Okay, so which means that we pick up a certain tetrahedron and one of the dihedral angles of that, right? So mu is this, and this is the Poisson bracket. Okay, X prime, and a Poisson bracket, and this is a Poisson bracket, is a Neumann-Zagier Poisson bracket. Which is defined as follows. defined by alpha beta equal 1 if alpha beta belong to one and the same tetrahedron and arranged in this clockwise way, and zero otherwise. Okay, so that's a gauge equivalence. Somehow not very transparent notion maybe, but it is defined like this. And now here is a main theorem of the course. Theorem. Okay, so let X be a shaped triangulation okay, so, without boundary.
I'm sorry, for some bracket, should it be isometric?
Yeah, it is.
So if it's like the other way around?
Yeah, so beta alpha will be -1, of course. Yeah. So because it's a Poisson bracket. So all properties of Poisson. So this is a minimal way of defining it. So you see, if we draw gamma here, so the gamma alpha will be 1, alpha gamma will be -1, and so on. Okay, the theorem, let X be a shaped triangulation without boundary. So without boundary is just to simplify the formulation. But it is TQ of T, so one can formulate the version with boundary such that H2 of X minus X0 is trivial. Then the partition function, so that's a definition of a partition function of X defined by ZB of X, B because we have a deformation parameter which enters through Faddeev function. So it's an integral of r power x2, integration of real variable sitting on the faces, product of tetrahedra in x3 of tetrahedral weight functions in state. So we have a coloring of all faces by real numbers. And we can calculate the tetrahedral weight function. We take the product of all tetrahedral weight functions and integrate over all colorings. That's the partition function. E is well defined. Is well defined. Element of set of complex numbers is well defined. And ZB of X equals ZB of X prime up to phase, which means that the absolute value of ZB of X equals absolute value of ZB of X prime if X and X prime satisfy one of the following conditions. So condition number 1 So the underlying triangulations, of x and x prime differ by the orientation of an edge. So this part tells simply that we can take any ordering locally for the vertices of the tetrahedron. So if we swap one of the arrows on a geometric edge, then we can recalculate the partition function, and then the absolute value will not change of that partition function. Okay, so that's the first part. Second part, if x and x prime are related by 2, 3 angled Pachner move. So angled Pachner move in the sense I described, that you have to relate the angles on two sides of the Pachner move by using the equations which I discussed. In particular, the edge which disappears when we pass from 3 tetrahedra to 1 should be balanced. If you remember, it was one of the conditions. And 3, if x and x prime are gauge equivalent. So that's the main theorem, which we will not prove because we don't have time. But having all the course, looking backward to the course, in principle, it should not be surprising, this theorem for you. Right? At least the Pachner move we discussed a lot, but the gauge equivalence probably it's a strange thing, and also 1. So 1 and 3 may be not evident, but 2 should be more or less clear because the weight functions were constructed the way that this Pachner move is satisfied. Okay, and then let me just put as a conjecture. This is really a conjecture which is checked on many examples, but has not been proven in general. And it concerns the asymptotic quasi-classical behavior of that partition function and its relation with hyperbolic geometry. So I don't put any number because it is only one conjecture of the whole course. So I'll limit when b goes to 0, 2 pi b squared log of dB of x is given by minus volume of x, where volume of x is by definition a supremum of a gauge equivalence so what is it? So the sum of volumes of t for t in x3, sum of individual tetrahedra where x is a gauge equivalence class. A gauge equivalence, or its gauge equivalence class. So we pick up one gauge equivalence class of triangulations. So we can vary the angles, right? Staying in gauge equivalent. And so we just maximize this sum with respect to this choice. And this we call volume of X. So where volume of T is following explicit function. These are alpha, beta, gamma dihedral angles. Angles, L of X is a Lobachevsky function, log of 2 sine theta, absolute value d theta. Lobachevsky function. And this is a Milnor's formula for the volume of ideal hyperbolic tetrahedron. Okay, so everything is explicit. So, and conjecturally, the asymptotic behavior is controlled by such a geometric quantity associated with shaped triangulation. Okay, and then we have a few more minutes to see how this works in practice when we try to calculate, when we try to make actual calculations. Example of calculation. So let us take one tetrahedron, 0, 1, 2, 3, positive tetrahedron, and we color with angles alpha, beta, gamma, gamma, beta, alpha. So here is one single tetrahedron, and X is given by a quotient space of that tetrahedron with respect to identification of faces D0T, D3T, and D1T, D2T. Which means that, so this is F0, this is F1. So we have a 0 and 3 are identified. So here the face F0 and the same as F0 here.
Is it positive or negative, the 3?
Sorry?
The 2 and the 3 and the arrows.
Yeah, it's wrong. Thank you. F0 and then F1, F1. Okay, we have only two geometric triangular faces in the triangulation, and topologically, X1 is equivalent to 3 sphere. 3 sphere and 2 edges, and the first skeleton is given by wedge of two edges, E0, E1. This is the only vertex. So if we put T maps to X by a projection, topological identification projection, then the pre-image of E0 is given by just one single edge, 0, 3. Let me draw it. This is E0. And all others, T minus 1, E1 is X, no, T1 set theoretically. So all 5 edges are identified to another edge E1. Okay, so we have this, and just a remark: E0 is noted in S3 like the trefoil. So this is a kind of sophisticated triangulation. So this edge, when you look in the quotient space in S3, it is a knot, and it is a non-trivial knot given by a trefoil. Okay, and then what else? Yeah, the weights, edge weights. W of E0, so it's clear that it is given by one single dihedral angle, gamma. Right, and then W of E1 is the sum of all 5 other edges, which is one copy of gamma, which is the edge 1, 2, and twice beta and twice alpha. So 2 alpha plus 2 beta. So 5 edges in total, so which is the same as 2 pi minus gamma. So you see the weights on the edges are given by one dihedral angle. And so x and x prime are gauge equivalent if and only if gamma equal gamma prime. Okay, so we have a one parameter of gauge equivalence. We can increase beta and decrease by the same quantity alpha, keeping gamma fixed. So this is the gauge equivalence class. And yeah, and now we calculate the partition function. So the ZB of x, so it is x, or what was it? We have to take a kernel, x1, x3, w alpha gamma hat of x0, x2, but we have to equate, right? So x3 should be equal x0. So I put here x0, and the x1 should be equal to x2. So there are only two integration variables, dx0, dx1. So the integration over R2. So that's the partition function. That's the partition function, and then we can use the explicit formula for the kernel, which I wrote in the remarks. So there was a zeta0 of alpha gamma, undefined phase factor, and delta of. So we have to write x0 minus x1, which is x1, plus x2, which is x1 again. Okay. And then phi gamma beta of x3 minus x2. x3 is x0, x2 is x1. And the exponential factor 2 pi I x0, x2 minus x3. So x2 is x1 minus x3 is x0. Okay, integral over R2, dx0, dx1. And now you see that delta function equates x0 to 0, So we can eliminate so the exponential does not contribute. And we have only zeta 0 of alpha gamma integral over r phi gamma beta of minus x1 dx1. And as you see, this integral is absolutely convergent because this is the Fourier image of phi gamma alpha at 0. So this is a zeta 0 of alpha gamma of phi gamma beta tilde of 0. Right? Because there is no exponential factor, but otherwise it is a Fourier integral. And now we can use the formula for the Fourier transform of phi, which is zeta 0 of alpha gamma, zeta 0 of gamma beta times phi beta alpha of 0 without tilde. And but we are interested in only absolute value of the partition function, so zeta 0 does not do not count. So we have a phi beta alpha of 0. That's a result of calculation of the partition function, and now we can write out this explicitly. So what is this? So the absolute value of phi j function, phi b of so 0 plus I delta beta plus gamma. If we look at the formula which defines phi beta alpha, and then exponential which is proportional to x, but x is 0, so that's the only answer. But now we can express alpha plus beta as pi minus gamma because of the angle rules. So phi b of I delta of pi minus gamma. And as you see, this is a confirmation of the statement of the theorem that the partition function depends only on the gauge equivalence class of the triangulation, which is determined by the value of gamma. But it does not depend on individual values of alpha or beta. Okay, and then that's the answer for the partition function. And then we can use, we can see if the conjecture holds in that case. So let us see how we handle this. Then we have the following asymptotic formula. So 2 pi I b squared log of phi b of x over 2 pi b limit. No, this is not asymptotic, but limit formula. Limit when b goes to 0. This is equal Euler's dilogarithm minus e power x. So this is an explicit function defined by this formula if absolute value of x is less than 1. Okay, so we have this asymptotic formula, and then we can use it to calculate the corresponding limit for the partition function we have calculated. So what we have to check, according to conjecture, we have to check the limit 2 pi b squared log of absolute value ZB of x. Limit when b goes to 0. So let us see what is this. So limit b goes to 0, 2 pi b squared log phi b of I. So now I put explicitly the form of delta, which was b plus b inverse over 2 pi. That's the delta. Pi minus gamma, absolute value. So we've got to calculate this limit. And on the log and absolute value can be exchanged. To pi b squared. So we can put the real part of log of phi b without absolute value. And now I put here this way, pi minus gamma over 2 pi b, 1 plus b squared. Okay, so we have this formula. And then we can even exchange real part with imaginary part. So imaginary part of limit 2 pi I b squared log of phi b I pi minus gamma over 2 pi b 1 plus b squared when b goes to 0. So I added I here and replaced the real part by imaginary part. And now if you look at this formula and at this, and at this formula. So you see 2 pi b in the denominator, 2 pi I b squared in the, as a front factor, and the b goes to 0. The only difference is 1 plus b squared. But when b goes to 0, 1 plus b squared goes to 1. So we can neglect b squared, and so safely use the right-hand side of the formula. So we obtain the imaginary part of Euler's dilogarithm E minus I think it's okay. E to minus this part, I pi minus I gamma. So it is an imaginary part of Euler dilogarithm e to power minus I gamma. Okay, so and then you just exercise, but not for you maybe, because there is no exercise session anymore. But you can just do it for yourself. This can be calculated to minus twice Lobachevsky function of gamma over 2. But on the other hand, volume of X, if we maximize maximum of lambda alpha plus lambda of beta plus lambda of gamma at gamma is fixed. So we can vary we can vary alpha and beta, keeping gamma fixed. And this is equal lambda of gamma, which is fixed, so it contributes. And then the maximum contribution is given by only in the case when alpha equal beta. So it is a twice lambda of pi minus gamma over 2. Okay, so achieve the maximum achieved when alpha equal beta equal pi minus gamma over 2. And this is equal twice lambda of gamma over 2. So, so you see that we exactly reproduce verify the conjecture, and it is satisfied for that example. And so you can remark tells that that the angles pi over alpha equal beta equal pi minus gamma over 2 correspond to complete hyperbolic structure on S3 with cone singularities. Okay, maybe I should take not S3 but R3 with cone singularities along E0 and E1 given by angles gamma and 2 pi minus gamma, respectively. So it is not just a hyperbolic structure in R3. It is a hyperbolic structure where it is a singular, because the angles do not sum up to 2 pi around the two geometric edges. So around E0, it is summed up to gamma, and on E1, it's a 2 pi minus gamma. So gamma is a geometric parameter here, so we can just see that there is a complete hyperbolic structure of cone manifold like this. And so our theory calculates a quantum partition function of that manifold, which asymptotically reproduces its volume. So I think that I stop here, so the course is over. I hope you enjoyed it. And so the rest of the course is the following. Now, 10 of you will pass the oral exam on 12th of June. So I repeat, but in the description of the course, it is described what kind of exam it will be. So there will be 2 questions, one theoretical from the list I put already on the web page, and there will be exercise of which will be much simpler than the exercises you encountered during the exercise sessions. But mostly they will be operator calculation within the L2 of R or R2, some matrix operator kernel, for example, or generalized trace. And maybe there will be some couple of geometric questions on calculation of lambda lengths within hyperbolic geometry. Okay, so you have to see what is the hyperbolic geometry in the upper half space. And you will have 30 minutes for 2 questions for preparation. So it's very much tight. as concerns. And then the organization will be, I will put on the web page a list of names with the order you will be passing the exam. So it will start at 8:30. The first person in the list will enter this room maybe at 8:30, start answering at 9. And at 9, the second person will enter for preparation, and during half an hour of exam for the first person, and so on and so forth, for 10 people. Closed, everything. Yeah, it's I mean, I had bad experience with open book. Okay, so I don't allow anymore. Okay, but it is don't be afraid. It will not be. You will not need to tell all the details. So the main thing is to see that you know what the subject is about, right? So that's okay. More questions? But we have some time for questions.
Talk about Topology TQT.
Yes.
It's not at all clear that what the relation to what you just said.
No, but this theorem gives what Topology TQT gives for closed manifolds, right, without boundary.
But it seems to depend a lot on the triangulation.
But the theorem tells that it does not, right? So the part number 2 tells us that it does not depend if you does not change if you apply 2-3 partner moves, and part 1 tells that it does not depend on actual ordering of the vertices. So you see the part 1 and part 2 ensure the topological invariance, but on the level of positive angles. So remember the angles here should be strictly positive. But there is a later version of the same TQFT which proves that positivity of angles is not an issue. So by analytic continuation, you can do any angles. So, the theory is really completely topological invariant. But it wasn't described in that course. But my purpose was to give an introduction to that theory. I hope I did it. Yeah, more questions?
What about the 1-3 partner move? I'm sorry.
Sorry?
What about the 1-3 partner move?
There is no 1-3 partner move because, as you see, the vertices it's not 1-3, 1-4, right?
Yeah.
1-4. Yeah, because the vertices are part of the data. You see here that somehow, so effectively the invariant is not of just a manifold, triangulate manifold. It's the invariant of a pair of a 3 manifold and a weighted graph given by unbalanced edges. And then, so the vertices make part of that graph. And that's why we don't impose any invariance on 1-4 partner move, because the vertices make part of the data. Yeah, this might reflect that the theory is not complete. So it is defined on a restricted class of 3 manifolds. So it remains to find out the more complete version of it. More questions? Okay, then thank you once more for following up to this point, and see you on exam and on 12th of June.